Welcome back, folks, and the topic of today's video is going to be Lewis dot structures of atoms. And we're going to show how these dot structures can then be used to show how bonding processes occur, both in terms of covalent and ionic bonding. So we'll review that just a bit as well. So first of all, if I want to make a Lewis dot structure of a particular element, what I want to do is to use dots around that element symbol to represent only the valence electrons. Now the reason why we do this is because, as you'll recall from lecture, only the valence electrons are involved in the bonding process, whether it's the formation of an ionic bond or the formation of a covalent bond. The core electrons do not matter. All right, so this is a shorthand way so that we can represent only the valence electrons that are, again, taking part in the bonding process to the exclusion of all the other core electrons. So here's how we do it. So I'm going to start out, for example, with the elemental symbol from hydrogen here. Now I know that hydrogen has a 1s1 configuration, so that means I have a 1s orbital with just a single electron in it. Now that single electron, since I don't have a full shell, is a valence electron. So what I'm going to do is I'm going to represent an electron as a dot around the hydrogen here. Okay, so that's my single 1s electron. Now if I go to helium, which is the next element, I pick up another electron. And what I do here, of course, is to fill up the 1s2 orbital. So I'm going to show that by pairing the electrons up here next to helium to signify again that I have filled an orbital in this case. Okay, in this case the 1s2. Now, what I can do for other main group elements is exactly the same kind of thing. So I would figure I'd just move along to the second row of the main group elements, and we can see where we end up as we continue to do this. Lithium working all the way across to neon. So in each case, what we have is the helium core. Okay, so we filled, in the case of helium, the n equals 1 principal energy level. Okay, so we know now that if we go beyond helium, any electrons that we put into the first row are going to be new valence electrons. All right, so we're going to start out with the helium core here. So with lithium, I'm going to bring in a 2s electron here. So I'm going to represent that as a single dot around the lithium. Now, when I move across to beryllium, I'm picking up one more proton. I'm also picking up one more electron. In this case, I'm again filling a 2s orbital. So as I did in the case of helium, what I'm going to do is I'm going to show that with a pair of electrons. But now that we're in the n equals 2 level, we're not done yet. We still have a set of 2p orbitals that we have to fill. Remember, we have 3 of them, so we can accommodate up to 6 more electrons. So as I move across to boron, I've got my 2s2 that I started with the beryllium, and now I'm going to add a 2p electron here. So I'm going to represent that as a third dot underneath. Moving on to carbon, we're going to get another p electron for a total of 4. So here's my 2 paired 2s electrons here. And now here's a p electron, another p electron, and that takes me to my 4. Now again, I'm not pairing up here because remember those p orbitals are degenerate. So I'm going to go around the atom first, then I'll come back and pair up. All right, so we still have room for one more unpaired p electron. That happens with nitrogen. So we have a 2s2, 2p3 configuration. Here are the two 2s electrons. Okay? Now I go to a 2p, a 2p, and a 2p. Okay? Each in its own degenerate orbital. Now, I move on to oxygen. I get 6 electrons total. Now I got to start pairing up in the p orbitals. So 1, 2, there are my 2s electrons. 3, 4, 5, and now I'm going to come back and I'm going to pair up in one of the p orbitals. Fluorine will have a total of 7 electrons. So here are our 2s electrons here. And I'll go 3, 4, 5, 6, 7. Okay, so now we have all the orbitals filled except for the one last p electron, which can handle one more electron. So now when we get to neon, we're back to a noble gas configuration. We will have filled out the n equals 2 principal energy level. So now we go 1, 2, 3, 4, 5, pair up, 6, 7, 8. All right? So the key to this when we generate these things is if we're talking about helium, we end up with what's called a duet. All right? So that means that that's going to be a stable configuration because we're in the n equals 1 level. Now if we go to the n equals 2 or the n equals 3 level, to be full now for main group elements, now what we have to achieve is an octet, or 8 electrons, in order to get to the noble gas configuration. Okay, so anytime we see that noble gas configuration, a helium, a neon, an argon, a krypton, a xenon, you get the idea. We know that we are in the most stable configuration because we have a full outer shell. Okay, so now what we can do is use these shorthand representations to see how bonding takes place. So let's use dot structures here to show how some bonds form. Now you'll remember we have two types of bonding. We can talk about the formation of an ionic bond, or I can talk about the formation of a covalent bond. What you'll remember in the case of the ionic bond is that it's a metal combining with a non-metal. And remember, the goal of each species is to get to a noble gas configuration. So we know that metals over on the left-hand side of the table like to lose electrons to look like the next previous noble gas. And we know that non-metals like to gain electrons to become the next noble gas. All right? So we can show that here. So let's assume I have a gas phase sodium atom, and I'm going to let that combine with a gas phase chlorine atom here. And again, we're going to look at each one's configuration. So sodium will be a neon core with a single 3s electron in it. Chlorine will be a neon core with an almost full set of 3p electrons here. Okay, so again, what we're trying to do is to fill out octets if we can. All right, so in this case, sodium we know is going to become happy to lose an electron. It's easier for it to lose its 1 than to gain 7, right? So what ends up happening is the chlorine here steals the electron from the sodium. So I can show the electron from the sodium now going over here to the chlorine to fulfill its octet. All right? And where does that leave us? Well, with regard to the sodium, that leaves me with a sodium ion with a neon configuration. That's its previous noble gas. We know it's stable there. Now, what else do we get? Well, when the chlorine atom gains that electron from the sodium, literally steals it. It's Grand Theft Auto here. All right, so we end up with a chloride ion with a 1- charge with a full octet. So now the sodium ion, 1+ looks like neon. It's happy. Chloride now has its octet. It's got a 1- charge. It looks like argon, and it's happy. Now, when I draw this thing, I always show the brackets around the anion to show that the octet here around the anion fully belongs to the anion, and there's no possession of any of these by the cation. So that's what those brackets there represent. Okay, so that's the formation of an ionic bond. And remember, what holds the ionic bond together is the electrostatic interaction now that occurs between the 1+ and the 1- here on each ion, because we know that opposite charges attract each other, and that's what binds these two ions together. Now, what about the covalent situation? Well, the simplest covalent bond I can make would be one between two hydrogens. And remember, in the case of covalent bonding, we're sharing electrons, again, to try to get each atom to a noble gas configuration. Now, we start out with each individual hydrogen. Each one has a 1s1 configuration. That means, in terms of its Lewis structure, it's a single hydrogen atom with a single electron in that 1s orbital. So now, since one hydrogen can't really steal an electron from the other hydrogen, the best way for these two hydrogens to be happy is to actually share these electrons. So that's how a covalent bond forms. Now, I can show a covalent bond this way, where I show the electron pair now being shared between the two hydrogen atoms. There's no brackets there, so we're assuming that the electrons are being shared. Now, if they're being shared, I can say now that this hydrogen at any given moment can lay claim to both of them. And if we lay claim to both of them, now I get a 1s2 configuration, which looks like helium. That hydrogen is now stable and happy. Likewise, I could say at any moment in time, the second hydrogen on the right could lay claim to both of those electrons. So now that hydrogen also has a 1s2 configuration, which also is helium, which makes it happy. Okay, so now we've been able to show that I can share electrons by way of these Lewis dot structures to form these stable covalent compounds. All right, so we're going to practice more with Lewis structures, primarily looking at Lewis structures of covalent compounds when we get back on Monday. All right, so we'll see you then.